Hey everyone! Buckle up because today we're diving into the weird, wild, and totally shocking side of science. Get ready to have your mind blown with 10 facts that will make you see the universe in a whole new light. Diamonds might be a girl's or guy's best friends, but did you know it rains diamonds on some stars? Inside certain white dwarfs, the pressure is so intense it squeezes carbon atoms together, forming solid diamond crystals. Imagine a cosmic downpour, not of water, but of sparkling diamonds. Of course, it's not that clear and simple, so let's deal with it. The idea of stars raining diamonds might sound like something out of science fiction, but there's actual science behind this concept. Stars like our sun eventually exhaust their fuel and collapse inwards. The outer layers are expelled, forming a planetary nebula, while the remaining core shrinks to become a white dwarf, an incredibly dense ball of leftover stellar material. The immense gravity within a white dwarf squeezes its atoms together into a special state called degenerate matter. Electrons are crammed into their lowest possible energy levels, and the Pauli exclusion principle prevents them from occupying the same state. By the way, how diamonds are born. During a star's life, it fuses lighter elements like hydrogen into heavier elements, including carbon. In a white dwarf, this carbon remains suspended within the degenerate electron gas. As the white dwarf cools and loses heat, its internal pressure continues to rise due to its immense density. When this pressure reaches a critical point, it can trigger a phase transition. Under the extreme pressure, the carbon atoms in the white dwarf rearrange themselves into a highly ordered crystal lattice structure, the signature of a diamond. The conditions necessary for diamond rain involve the behavior of degenerate matter, a unique state of matter found only in white dwarfs and neutron stars. Understanding this process helps us explore the properties of matter under extreme pressure. While directly observing diamond rain on a white dwarf might be challenging, the concept highlights the incredible forces and processes at play within stars. Black holes are often depicted as cosmic vacuum cleaners, relentlessly pulling in anything that gets too close. But a fascinating, yet highly speculative, theory proposes a different story: black holes as the potential creators of entirely new universes. Let's take a deeper look into this mind-bending concept. Black holes are regions in space-time where gravity is so intense that not even light can escape. They form when a massive star collapses in on itself, crushing its core into an infinitely dense point called a singularity. Surrounding the singularity is a boundary called the event horizon. Once something crosses this point, the escape velocity exceeds the speed of light, making escape impossible. Our understanding of physics breaks down at the singularity. However, some physicists propose that instead of a point of infinite density, the singularity might be a bridge or doorway to another spacetime. Wormholes are hypothetical tunnels that could connect two distant points in spacetime, or even two different universes. The intense gravity of a black hole could theoretically distort spacetime enough to create a wormhole on the other side of the singularity. Another theory suggests that the immense pressure within a black hole could cause a bounce effect. Instead of collapsing infinitely, the singularity could trigger a reversal, leading to the expansion of a new universe on the other side. While its validity remains uncertain, the theory of black holes creating new universes pushes the boundaries of our cosmological understanding. It forces us to consider alternative possibilities for the origin and fate of our universe. This theory connects to the idea of a multiverse, a collection of multiple universes existing alongside our own. If black holes can create new universes, they could be a potential mechanism for the formation of a vast and diverse multiverse. Black holes remain shrouded in mystery, but the possibility of them giving birth to new universes is a captivating concept. While it might be science fiction for now, it highlights the beauty of scientific exploration and the vast unknowns that lie beyond our current knowledge. Imagine Earth not bathed in the azure glow we know today, but shrouded in a hazy, violet light. This wasn't a scene from a fantasy novel, but a possible reality of our planet billions of years ago. Here's a deeper dive into the science behind a purple Earth. Around 4 billion years ago, Earth's atmosphere was vastly different from the one we breathe today. It lacked free oxygen and was dominated by gases like methane, ammonia, carbon dioxide, and water vapor. The key difference? The absence of abundant oxygen molecules. Today, oxygen in the upper atmosphere scatters blue light from the sun, giving our sky its characteristic color. Without oxygen, this scattering wouldn't occur. Primitive life forms, likely bacteria, emerged on the early Earth. These ancient microbes used a different type of photosynthesis than plants do today. They didn't produce oxygen, but instead relied on a molecule called retinol. Retinol, found in some bacteria today, absorbs green and yellow light from the sun. The remaining unabsorbed light, a combination of red and blue wavelengths, interacts with the atmosphere to create a purplish hue. So, why planet turning blue? Around 2.4 billion years ago, a turning point arrived. Cyanobacteria, a type of bacteria that releases oxygen as a byproduct of photosynthesis, began to thrive. Over millions of years, they gradually produced enough oxygen to change the atmosphere's composition. With the rise of oxygen, a new player entered the game. Oxygen molecules in the upper atmosphere started scattering blue light from the sun more efficiently, leading to the development of the familiar blue sky we see today. The idea of a purple Earth challenges our perception of our planet's history. It highlights the dynamic nature of Earth's atmosphere and the crucial role of life in shaping its current state. Uranus and Neptune, the distant ice giants of our solar system, might hold a surprising secret beneath their thick, swirling atmospheres. Theories suggest the existence of vast, hidden oceans unlike any found on Earth, oceans of superheated liquids under immense pressure. While Uranus and Neptune appear blue due to methane gas in their atmospheres, they are far from gassy giants like Jupiter and Saturn. Moving deeper inward, scientists believe the composition transitions from hydrogen and helium to a region dominated by water, ammonia, and methane ice. Despite their immense distance from the sun, Uranus and Neptune radiate more heat than can be solely explained by solar radiation. This suggests an internal heat source, possibly leftover from their formation or from the decay of radioactive elements within their cores. Let's move on to the birth of a hidden ocean. The immense gravity of these ice giants creates tremendous pressure within their interiors. This pressure, combined with the internal heat, is theorized to melt the ices of water, ammonia, and methane, forming a unique liquid layer. Unlike Earth's oceans, these wouldn't be composed primarily of water. They would be a superheated slush of water, ammonia, and methane, existing at extremely high temperatures and pressures. Imagine a boiling ocean under a layer of ice, a truly alien environment. The combination of water, ammonia, and methane in these oceans could create a rich and complex chemical soup. Scientists speculate that this environment might be conducive to exotic forms of chemistry, potentially leading to the formation of prebiotic molecules. However, the extreme conditions within these oceans, including the high pressure, temperature, and likely absence of sunlight, make it highly unlikely that life, as we know it, could exist there. The possibility of hidden oceans on Uranus and Neptune paints a fascinating picture of our solar system. It highlights the diversity of planetary environments and the potential for exotic and unexpected discoveries beyond Earth. It might come as a surprise, but your body is teeming with a hidden population, bacteria. In fact, there are trillions more bacteria residing within you than human cells. Estimates suggest that the human body is home to around 30 trillion human cells. However, the bacterial population dwarfs this number, reaching a staggering 39 trillion. This means, on average, for every human cell, there are about 1.3 bacteria residing within or on you. These bacteria aren't just hanging out loosely. They thrive in various niches throughout your body, with the most abundant communities residing in your gut, mouth, and skin. While some bacteria can cause illness, the vast majority of these microbes are beneficial or even essential for our health. They form a complex ecosystem known as the human microbiome, playing vital roles in various bodily functions. The gut microbiome, for example, aids in digestion by breaking down complex carbohydrates and producing essential nutrients. It also helps regulate the immune system and protects against harmful pathogens. Similarly, the skin microbiome helps maintain a healthy barrier against harmful microbes and regulates moisture balance. The mouth microbiome plays a role in oral health by preventing the overgrowth of harmful bacteria. The human microbiome is a delicate balance. Factors like diet, stress, and antibiotic use can disrupt this balance, leading to health problems. A healthy microbiome is a diverse microbiome. A rich variety of bacterial species ensures a robust and resilient ecosystem. While the idea of having more bacteria than human cells might seem strange, these tiny organisms play a crucial role in our health and well-being. Understanding and nurturing this complex ecosystem is key to maintaining a healthy body. Even more shining facts await for you. Imagine a celestial body not composed of rock and ice, but of a mind-boggling abundance of diamonds. While it might sound like something out of science fiction, astronomers theorize the existence of such diamond planets. Let's explore the science behind this fascinating concept. With the discovery of thousands of exoplanets, planets outside our solar system, astronomers are constantly searching for planets that share similarities with Earth. One category of interest is super-Earths, rocky planets with masses several times greater than Earth. The immense gravity of a super-Earth creates tremendous pressure within its interior. This pressure, along with the high temperatures, plays a crucial role in determining the physical state of the materials that make up the planet. Scientists believe that some super-Earths, especially those rich in carbon, could have conditions suitable for diamond formation. Under the immense pressure and high temperature within their interiors, methane ice, a potential component of these planets, could be squeezed and transformed into a super-hard form of carbon, diamond. Some theories even suggest that the immense pressure could trigger a form of diamond rain, where liquid carbon within the planet precipitates as diamond crystals that sink towards the core. Our sun might seem like a solitary star, radiating warmth and light. But the truth is, the sun isn't afraid to get a little close and, well, borrow some gas from its neighbors. Here's a deeper dive into this surprising phenomenon of stellar gas exchange. Stars are born, live, and die within vast stellar nurseries called nebulae. These regions are densely packed with gas and dust, and young stars often find themselves in close proximity to each other. Even though stars are immense, their gravity isn't infinitely strong. As stars move within a nebula, their gravity can tug on the gas and dust surrounding them. When two stars pass close to each other, their gravitational pull intensifies. This can lead to a situation where one star, typically the more massive one, can pull gas away from its neighbor. Imagine two dancers twirling, with one grabbing hold of the other's scarf and pulling it loose. Our Sun, while not the biggest star in the galaxy, is certainly not shy. Throughout its lifetime, it has likely interacted with other stars in its stellar nursery, potentially acquiring some of their gas through gravitational interactions. The Sun relies on nuclear fusion, converting hydrogen into helium, to generate its light and heat. The stolen gas, rich in hydrogen and other elements, can contribute to the Sun's fuel supply, influencing its overall lifespan and energy output. The composition of the stolen gas can be slightly different from the Sun's original gas. Over time, this can subtly alter the Sun's overall chemical makeup. While Earth's fiery mountains and lava flows might be the first thing that comes to mind when we think of volcanoes, volcanic activity isn't exclusive to our planet. Our solar system is teeming with evidence of past and even ongoing eruptions on moons, planets, and even dwarf planets. Let's explore the fascinating world of extraterrestrial volcanoes. Similar to Earth, some extraterrestrial volcanoes erupt with molten rock or silicate lava. However, the composition of this lava can vary depending on the volcanic body. These volcanoes erupt with a different type of lava, ices, and other volatile materials like water, methane, or ammonia. These eruptions can create bizarre landscapes on moons and dwarf planets. Jupiter's moon Io is the most volcanically active body in our solar system. Hundreds of volcanic plumes erupt from Io's surface, spewing sulfur dioxide and other materials. These eruptions are fueled by tidal heating, where Io's constant tug-of-war between Jupiter and other moons creates immense internal friction. Europa, another moon of Jupiter, is covered in a thick, icy crust. While there's no direct evidence of volcanic activity on the surface, some scientists theorize the existence of a vast ocean of liquid water beneath the ice. Hydrothermal vents spewing out water and minerals from the ocean floor could potentially be a form of cryovolcanism on Europa. Mars is home to the largest volcano in our solar system, Olympus Mons, a colossal shield volcano towering over 21 kilometers high. While Martian volcanoes are currently dormant, vast lava plains and volcanic calderas, collapsed volcanic craters, paint a picture of a once intensely volcanic planet. Venus, our closest neighbor, is shrouded in a thick, hot atmosphere. While direct observation of volcanic activity is difficult, radar data suggests the presence of numerous shield volcanoes and volcanic plains. The scorching Venusian surface temperature, hot enough to melt lead, might keep these volcanoes simmering even today. Ceres, the largest dwarf planet in the asteroid belt, has surprised scientists with evidence of cryovolcanic activity. Recent observations suggest the presence of bright water vapor plumes erupting from Ceres' surface, hinting at a possible internal reservoir of liquid water and potential cryovolcanic activity. The discovery of volcanoes on other planets and moons expands our understanding of geological processes beyond Earth. It highlights the dynamic nature of celestial bodies and the potential for fascinating discoveries waiting to be made in our cosmic neighborhood. Imagine a planet not with continents and oceans, but entirely composed of water, a vast, swirling sphere of liquid. These hypothetical ocean planets are a fascinating concept in exoplanet research, pushing the boundaries of what a planet might be like. The discovery of thousands of exoplanets has revealed a remarkable diversity in planetary compositions. While rocky planets like Earth are common, scientists are also exploring the possibility of planets with unique compositions, like those dominated by water. Water is one of the most abundant molecules in the universe, found in gas clouds, comets, and even within stars. It's possible that under certain conditions, planets could form with water as the primary constituent. The leading theory for ocean planet formation suggests the gradual accumulation of icy material, including water ice, ammonia ice, and methane ice, from a protoplanetary disk. As the planet accumulates mass, its gravity increases, leading to immense pressure within its interior. This pressure can melt the ices, forming a vast ocean of liquid water extending all the way to a rocky core. Unlike Earth, where water is concentrated at the surface, an ocean planet would have water as its dominant component. The ocean on an ocean planet would be incredibly deep, with immense pressure at the core. The composition of this ocean might not be pure water. It could be a superheated liquid mixture of water, ammonia, and other elements. With no solid surface, weather patterns on an ocean planet would be vastly different from Earth's. Giant storms and waves could churn the vast ocean depths, creating a dynamic and potentially turbulent environment. Currently, directly observing the composition of an exoplanet is difficult. Scientists rely on indirect methods like studying the size, mass, and atmospheric composition of a planet to infer the possibility of a water-dominated world. Thick atmospheres rich in water vapor can sometimes mask the true composition of a planet, making it challenging to definitively identify an ocean planet. While the confirmed existence of an ocean planet remains elusive, the possibility itself is a captivating consequence of the diverse conditions that can exist during planet formation. The search for these exotic worlds continues, pushing the boundaries of our knowledge about exoplanets and the potential for unique planetary environments. Imagine an object so dense that a teaspoon of its material would weigh billions of tons on Earth. That's a neutron star, the collapsed core of a massive star. One of their most surprising features? Their surfaces are incredibly smooth, arguably smoother than anything you've ever encountered. When a massive star runs out of fuel and explodes in a supernova, its core undergoes a dramatic collapse. The immense gravity overcomes the outward pressure, squeezing the core's protons and electrons together to form neutrons. This crushing force creates a superdense object called a neutron star, typically around 10 to 20 kilometers in diameter, but with a mass exceeding our Sun's. The immense gravity of a neutron star plays a key role in its smoothness. Imagine a bumpy, uneven surface on the neutron star. The tremendous gravitational pull would act on those bumps and irregularities, pulling the material inwards until the surface becomes incredibly smooth. Another factor contributing to smoothness is a principle called degeneracy pressure. Degeneracy pressure arises due to the quantum behavior of neutrons crammed together in the star's core. This pressure acts like a repulsive force, resisting any further compression and maintaining the smooth surface. The extreme smoothness of neutron stars helps scientists test the predictions of general relativity, Einstein's theory of gravity. Any deviations from perfect smoothness could indicate limitations in our current understanding of gravity under such extreme conditions. The remarkable smoothness of neutron stars is a testament to the powerful forces at play in the universe. It highlights the extreme conditions within these celestial objects and provides valuable insights into gravity and the nature of matter. That's all for today. Hope you enjoy this video. If you do not agree with any information or have clarifications or questions, I will be glad to see them in the comments under the video. Don't forget to subscribe to the channel so that you don't miss the next video.